In this session, we will begin to study another tissue response to injury, degeneration. These are the learning objectives for today. You should be able to define degeneration, state the causes of different types of degeneration, compare and describe the morphological appearance of different types of degeneration. Cell injury occurs when stimuli are so severe that cells are no longer able to adapt. Injury may progress from a reversible state to an irreversible stage. Reversible cell injury, which we call degeneration, infers that the damager can be repaired. If the injurious stimulus abates, the cell will return to normal. Persistent or excessive injury drives cells into an irreversible state, leading to cell death. Necrosis and apoptosis are two usual pathways of cell death. When cellular injury is reversible, sublethal, and sustained, cells and tissues tend to accumulate substances in abnormal quantities. These substances may be normally found in the body or are not found in the body under normal conditions. They may be stored inside the cells or in extracellular locations. Degeneration describes morphology, the type of substance that accumulates, and the pathogenesis of different types of degeneration vary. The morphological responses to reversible cell injury can be in several forms. Here, we will merely discuss edema, fatty change, hyaline change, mucoid degeneration, and pathological calcification. There are several terms used to describe edema, such as hydropic change, vacuolar degeneration, or cloudy swelling. It is the excess accumulation of water inside the cells and the first manifestation of almost all forms of cellular injuries. Intracellular edema is a common response to many different etiological factors, including lack of oxygen, toxic agents, and osmotic effects. These factors all cause damage to mitochondria and their enzymatic pathways, leading to decreased formation of ATP. This makes less energy available for all the energy-requiring reactions in the cell. In particular, this leads to failure of the sodium pump, which is located in cell membranes. Sodium retention results in water accumulation in the cell. When it affects many cells in an organ, one will find the organ to become pale, tensely swollen, and heavier. This is the gross appearance of an edematous kidney. The cut surfaces are turbid and swollen. The kidney looks like it has been scalded by hot water. Here, we should pay attention to the gross morphological features, swollen and pale. Histologically, we can find the swollen parenchymal cells. Depending on different stages of edema, the morphology is different. The picture shows the histological appearance of the edematous kidney in an early stage. A fine granularity-like ground glass in the cytoplasm of the proximal convoluted tubule cells can be seen. Electron microscope showed fluid accumulation in the dilated mitochondria and endoplasmic reticulum, hence giving it the granular appearance. In the later stage, when more water accumulates in the cells, we call it hydropic degeneration. This is the hydropic degeneration of liver cells. We can see clear vacuoles in the cytoplasm. The swollen cells become balloon-like. This picture shows the different stages of cellular swelling. With the progression of edema, the morphology changes from granular degeneration to cytoplasmic puffing and ballooned degeneration. Hyaline change includes various intracellular or extracellular alterations. It appears as a homogeneous structural change in the tissue. Hyaline change is a description of the physical form. It is not a distinct chemical entity. These changes are diverse. The mechanisms will be discussed with each morphological type. Major types of hyaline change include intracellular hyaline change, collagenous fibrous tissue hyaline, and vascular hyaline change. Here are the common forms of intracellular hyaline change. In patients with proteinuria, the epithelium cells of the renal tubules show the histologic appearance of loud, pink, hyaline cytoplasmic droplets in HE stand sections. These droplets contain plasma protein reabsorbed from the urine. Injury to liver parenchymal cells can cause aggregates of cytokeratin filaments, appearing as very distinctive cytoplasmic hyaline droplets. It is commonly seen after injury due to alcohol. Another example is the marked accumulation of newly synthesized immunoglobulins in some plasma cells. For example, in the plasmacytoma, the tumor generates immunoglobulins stored in the cytoplasm as Russell bodies. All scars may appear hyalinized due to the hyaline changes in the connective tissue. Closely, it appears as a porcelain white area. Under light microscope, it appears as homogenized eosinophilic broad collagen fibers that forms as a result of abnormal collagen fiber cross-linkage. Vascular hyaline is commonly seen in arterioles of hypertension and diabetes, especially in the spleen, kidney, and brain. Vascular hyaline is due to extravasated plasma protein and deposition of basement membrane material. This photo shows vascular hyaline change of the splenic artery in a patient with hypertension. The wall of this arteriole shows a homogeneous pink hyaline signet with lots of structural detail and with narrowing of the lumen. Mucoid degeneration is the accumulation of mucin in interstitial tissue. Most commonly, this mucin is produced by connective tissue cells. Excessive production of connective tissue mucin is usually found after prolonged injury and repair, such as mucin overproduction by fibroblasts seen in lesions of atherosclerosis. Decreased thyroid function can cause skin connective tissue cells to produce increased amounts of mucopolysaccharides in the dermis. This leads to a thick appearance of the skin called mesoderma. Tumor-derived mucin, such as cardiac myxomas, soft tissue myxomas, are composed of cells that produce excess connective tissue mucin. Accumulation of connective tissue mucin are usually recognized under light microscope, where they appear as loose areas or spaces filled with mucin. This is a situation where the use of histochemical stains can assist with recognition. ocean blue stains or PAS diastase stains are especially helpful to identify connective tissue mucin. Here are the references and acknowledgement. This completes the first part on degeneration. Next time, we will discuss several other types of degeneration, fatty change, and pathological calcification. Thank you for your attention.